Hello guys, last time we saw how a difference amplifier works and how we can use it to amplify the difference between two signals. Now it's time to level up this circuit and see what we can do. So let's start. This is our current difference amplifier circuit. We have seen last time that this circuit amplifies the difference between two input signals while rejecting any input which are common. These common mode signals are called common mode noise, and the property of cancelling out any signals that are common is known as common mode rejection ratio. But it had some limitations. First, the impedance of the inverting and non-inverting inputs are relatively low and unequal. Let's take our previous example. The input impedance to Vin is 10K, but for this Vin2, it will not be the same. Even though we add 10K at the non-inverting terminal, the impedance of Vin2 will be twice of that. So when voltage is applied to one input while grounding the other, different currents will flow depending on which input receives the applied voltage. And this unbalance in the source resistors will degrade the circuit's CMRR. Also, this circuit requires a very close ratio match between these resistor pairs. Otherwise, the gain from each input would be different, which again affects the common mode rejection. For example, at a gain of 1, with all resistors of equal value, a 0.1% mismatch in just one resistor will degrade the CMR to a significant level. In spite of these problems, this difference amplifier is very useful in applications such as battery cell measurement, where DC common mode voltage may be greater than the supply voltage. Now we'll see the advanced version of this difference amplifier and see how we can improve its performance. The idea is very simple. We can just add the buffer circuits at the input of this difference amplifier. And that's all. Well, here we can go one more step further. Let's weaponize this buffer circuit with some gain, which gives us more flexibility, and it would look something like this. We add multiple resistors, which increases the gain equally for differential signals. If you look closely, these op-amp circuits look like non-inverting amplifiers. Now we can refine this circuit mode, which will look something like this, and it is classic 3 op-amp instrumentation amplifier circuit, which we'll see in this video. Here we connect a single gain resistor RG between the junction of two input buffers by replacing two resistors. Now actual differential input voltage will appear across this RG because the voltage at the summing junction of each amplifier is equal to the input voltage applied to its positive terminals. So by changing this RG, we can simply change the gain of this instrumentation amplifier. There is one more advantage of this connection. Once the difference amplifier has been set up with the ratio match resistors, then we don't need to do any other resistor matching to change the gains. Normally, these amplifiers A1 and A2 will operate with gain and amplify the input signal. However, a common mode voltage is applied to the amplifier inputs. The voltage on each side of the RG will be equal, because both amplifiers will amplify the voltage at the same level. So no current will flow through this resistor. Since there is no current in RG and even through R5 and R6, amplifiers A1 and A2 will operate as just buffers. So common mode signals will be passed through as it is. But differential voltages will be amplified by this factor. This means that we may take as much gain as we want from this end by using RG without increasing the common mode gain and error. So the differential signal will be increased by gain, but the common mode error will not. so CMRR will increase drastically. Finally, because of the symmetry of this configuration, if there are any common mode errors by input amplifiers, the output difference amplifier will cancel it out. This is why it is superior in every way. If you have noticed, there is one terminal called as reference. There is usually one more called sense, but it's not important for now. By using this reference terminal, we can play with the ground connections. It allows an external offset voltage for the difference amplifier where we can change its reference potential. For normal conditions, the reference is connected to the ground. Now, let's see how we can design a circuit of 3 Opamp Instrumentation Amplifier. We give two signals which have some common mode voltage, and its different voltage will range from minus 0.5 volt to 0.5 volt. That means we have to amplify these 0.5 signals, not the common mode voltage. The required output needs to be from minus 5 volts to 5 volts range from this amplifier. And for this circuit, we can provide plus 15 and minus 15 volts VCC and VEE supplies. High value resistors can degrade the phase margin of the circuit and introduce additional noise in the circuit. So we have to choose the optimum resistor values. Now we'll start with the design process. If we keep these resistors R5 and R6, R1 and R3, R2 and R4 equal, then the transfer function, or say the relation between output and input voltage, would be like this, where the reference voltage is kept 0. So this is the output requirement. Now the required gain is like this. There are 4 unknowns in this equation. To make our life easier, we'll choose the same resistor values of R1, R2, R3, R4, R5 and R6 as 10K. Now we'll calculate the value of the gain resistor. As we know, the required gain is 10 volts per volt. Using this equation again, we can calculate the value of Rg, which is 2.2K. For the circuit, we'll use a TLV171 op-amp. We can also simulate this circuit using TI software from TI. I've added the link of the simulation files in the description. This is how simply we can design an instrumentation amplifier. We can use this type of amplifier using a Wheatstone bridge resistor network like this. This type of circuit is very useful where there is a small signal and the environment is too noisy, but the signal needs to be very accurately measured, such as medical instruments like blood pressure sensors, ECG or EKG machines, and heart rate monitors. These things need a precise measurement. And that's the wrap. I hope you picked up something useful from this video. The reference of this design is added in the description below. While checking the reference, don't forget to hit that subscribe button as well. It's right over there. I'll see you next time. Till then, stay hungry, stay foolish.